Hello everyone, my name is Chieh-Yun Chen. Today, I'm excited to present our work on image-based multi-pose virtual try-on. We are from National Jiao-Tong University, and we are the winner team of the fourth Look into Person Challenge within Track 3. This work is jointly advised by Professors Honghan Shuai and Wenhuang Chen. The core technology of this work is based on our own oral paper in ACM Multimedia 2019, with the paper title Fashion on Semantic Guided Image-Based Virtual Try-On with Detailed Human and Clothing Information. First of all, I will give a brief introduction. Next, the detailed architecture of our try-on solution. Third, the results of the experiment. And the last, conclusion. E-commerce brings more and more convenience for our daily life, and is growing at a phenomenal rate. However, within the fashion industry, most people tend to shop offline rather than shop online. As the figure shows, 92% of the people would like to go offline shopping, which is quite significant. Because there exist differences between the fashion items online and the real ones in a physical shop. For example, the color of clothing may differ. The model online can represent the body shape of the users, or the size of the clothes are not clear online. Therefore, virtual try-on network is essential to help shorten the gap between the online and offline shopping experience. Also, as a situation like the coronavirus outbreak, it is more and more important to bridge the gap between online and offline shopping. For our work, we devoted to the multi-pose virtual try-on work for giving the customer more information to decide whether the garment is suitable or not. We apply the concept of curriculum learning and design a semantic-guided learning to advance both qualitative and quantitative results of virtual try-on, and also solve the human limbs occlusion problem commonly existed among the state-of-the-art virtual try-on systems. The most significant improvement is to preserve the clothing details precisely. To simplify the task of multi-pose virtual try-on, we built our network with three following stages. First, pose-guided parsing translator. Second, segmentation region coloring. And the last, salient region refinement. Let's talk about the details of the stages. In the first stage, pose-guided parsing translator aims to transform the human posture in semantic guided form and simultaneously try on the target clothing mask, which helps to learn the clothing type and generate a result in semantic segmentation form. We first drop the information of the source human image into semantic segmentation form and make the target clothing image into the target clothing mask. Concatenating these two and also the key point of the target pose as the input of the conditional GAN, we generate the target human in semantic segmentation form. Here, we adopt GAN loss and binary cross entropy loss. Then, in the second stage, segmentation region coloring, we render the natural human information back to generate the rough results with human appearance based on the transformed semantic segmentation region from stage 1. We first adopt the source human mask to filter out the clothes from the source human to prevent the source clothing information from affecting the target clothes. Then, concatenate the transformed segmentation region from stage 1, in-shop clothing and source person image without clothes as the input to generate the rough results. The objective function is a GAN loss and also L1 loss, where the GAN loss is calculated by the binary cross entropy loss, since it will help force the GAN to concentrate on the binary problem as true or false. We pair the course result IG and the source image IS to encourage the discriminator to distinguish the difference between generated result and target result, instead of only the distinction between the synthesized image and the natural image. Further, we adopt L1 loss to capture the global structure information. In the third stage, Salient Region Refinement, we focus on 3 critical regions: face, clothing region, and the lower body part, to render more detailed information to make the try-on results more real. For virtual try-on, the quality of it highly depends on the characteristics of users, for example, face details, skin color, or body shape. Also, the clothing information is critical, for example, clothing texture, logo, or strip, and 3D representation like shadow and pleat is also important. Therefore, we designed 3 refinement subnetworks for face, clothing region, and lower body parts to synthesize the detailed information for generating lifelike results. For face refinement, we modify the conditional gain in stage 2 by removing the fully connected layer, which helps to preserve the input detail when compressing. We use the body part mask to extract the head region from the source image and the generated image from stage 2. Concatenating these 2 images to generate the residual image to add for more detailed information. The loss function of the generator are VGG perceptual loss, local L1 loss, global L1 loss, and also gain loss. The local L1 loss is to inhibit the artifacts caused by the VGG perceptual loss, and the global L1 loss ensures that residual information can merge into the coarse result image. For clothing refinement, we use body part mask to extract the clothing region from stage 2 and from source image. In this refinement, we use 3 encoders to extract different information. For the first encoder, which is on the top of the figure, it extracts the global feature from the in-shop clothes. As for the second encoder, it extracts the primary information from stage 2 results. And for the third encoder, concatenating the 3 clothing images as input, it extracts the global transmitted trend in pixel level. For example, it would detect the flow from the source image to the generated image, and the mask representing whether the information of generated position exists in the source. After getting the critical information, we use an attention module to match the information and generate the refined clothes. The loss functions are VGG perceptual loss, local L1 loss, and global L1 loss. Here is worth mentioning that we exploit the body part mask to precisely extract the clothing region. Therefore, we can fuse the refined clothes to the coarse result without veiling the human limbs in front of the clothing region. For lower body refinement, we use the body part mask to extract the lower body part from stage 2 and from source image. Then, using 2 encoders to extract both features from source pants and coarse pants from stage 2, and concatenate the 2 features to the decoder and generate the refined pants. The loss functions are VGG perceptual loss, local L1 loss, and global L1 loss. Let's talk about the experiment. Here demonstrate a part of our result. The top row represents the source human image, and second row indicate the target clothes. The third row are the target posture. The fourth row shows the unrefined try-on results, and the last are the refined results. These results show that our model can try on various kinds of clothes like long sleeves, t-shirts, and vests containing complicated patterns. Also, it preserves well for different clothing length transform. For example, in case 2, 3, 4, 8, and 13, it transforms from short sleeves to sleeveless t-shirt. Further, it can keep the texture and cloth color for the lower body parts. For example, in case 11, it preserves the black skirt, which is the rare case in the training dataset. In general, our model generates a reasonable body shape, skin color, hairstyle, and also human characteristics. Then, we talk about the case that preserves specific details well. For example, in case 2, it preserves the thin necklace. Case 5 keeps the embossed logo. In case 6, the blue-red design in specific position matches the in-shop clothes. Case 7 to 9 keeps the detail pattern quite the same as the in-shop clothes. In case 10, it preserves the strip naturally. Case 11 to case 13 generate the specific logo quite the same as the in-shop clothes. For example, the text design in case 11, the pineapple in case 12, and the Adidas logo in case 13. The detail-preserving performance in our work surpasses the state-of-the-art virtual try-on works. In conclusion, the core technology of this work is based on our previous work Fashion On, published in ACM Multimedia 2019, and improves the generation of more detailed information to make the try-on results more natural. We divide the network into 3 stages. First, post-guided parsing translator transforms the source human parsing to the target post with in-shop clothing mask. Second, segmentation region coloring generates the clothes and human appearance based on the results from stage 1. And third, Salient Region Refinement precise the facial clothing region and lower body parts of the result from stage 2. In this work, we are able to generate high-quality try-on result in arbitrary poses. Also, the most critical improvement is that it preserves detailed patterns precisely. Thank you for listening. The following are our emails. If you have any questions, please feel free to contact us. Thank you for your attention.